Tonight, we're going to explore one of the most fundamental limits built into reality itself, the speed of light. Not just how fast it is, but why nothing can move faster, and what that reveals about the very fabric of space and time. This isn't just about light. It's about the maximum speed at which anything can travel, the ultimate cosmic speed limit that governs everything from the smallest particle to the largest galaxy. By the end of this journey, you'll understand why this speed limit exists, what happens when things approach it, and why breaking it isn't just difficult, it's fundamentally impossible. Before we dive in, if you find this kind of exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small gesture for you, but it makes a huge difference in helping me create more content like this. Here's what makes the speed of light so strange. In our everyday experience, there's no absolute speed limit. If you're on a train moving at 100 kilometers per hour and you walk forward at 5 kilometers per hour, you're moving at 105 kilometers per hour relative to the ground. Speeds simply add together. It seems obvious, natural, the way the universe should work. But at very high speeds, this breaks down completely. As you approach the speed of light, the rules change in ways that seem impossible, yet they're absolutely real. Time slows down for moving objects. Lengths contract in the direction of motion. Mass effectively increases. And no matter how much energy you add, you can never quite reach that ultimate speed. The speed of light is approximately 299,792,458 meters per second, or about 300,000 kilometers per second, if you prefer round numbers. That's fast enough to circle Earth's equator 7.5 times in a single second. Fast enough to reach the moon in just over 1 second. Fast enough to cross the entire solar system in a matter of hours. And yet it's not infinite. Light takes time to travel. 8 minutes from the sun to Earth. 4 years to the nearest star. Billions of years from the most distant galaxies we can see. The universe has a speed limit, and that limit shapes everything about how reality works. Why does this limit exist? Why can't things go faster? And what does it mean for space travel, for our understanding of the cosmos, for the very nature of time itself? These aren't just abstract physics questions. The speed of light limit affects GPS satellites, which must account for relativistic effects to give you accurate directions. It limits how quickly we can communicate with spacecraft exploring distant planets. It determines whether interstellar travel will ever be practical. It explains why we can never change the past, only the future. Over the next few hours, we're going to build a complete understanding of this cosmic speed limit. We'll start with the basics, understanding what light actually is, and how we first measured its speed. Then we'll explore Einstein's revolutionary insights about space and time. We'll discover why accelerating to light speed requires infinite energy, and we'll examine what this means for the universe and our place within it. So settle in, get comfortable, and let's begin this journey into one of the universe's most profound mysteries. The speed of light isn't just a number. It's the key to understanding how reality itself is structured. Let's start with something you experience every single day without thinking about it. The difference between instant and delayed. When you flip a light switch, the room seems to brighten instantly. When you clap your hands, you hear the sound immediately. When you see lightning and then hear thunder, you notice a delay. The light reaches you first, then the sound follows seconds later. You intuitively understand that sound takes time to travel, that it moves at a finite speed through air. But what about light? Does it travel instantly, or does it also have a speed? For most of human history, this wasn't obvious. When you look at something, you see it now. There's no noticeable delay between the moment you open your eyes and the moment you perceive the world around you. The sun rises, and you see it. A friend waves, and you see their hand move. Everything appears instantaneous. The ancient Greeks debated this question. Some philosophers, like Empedocles in the 5th century BCE, suggested that light must take time to travel. Others, including Aristotle, whose authority dominated Western thought for nearly 2,000 years, argued that light's presence was instantaneous, filling space immediately without traveling through it. There was no way to test these ideas with the technology available at the time. The question remained philosophical rather than scientific. If light did have a speed, it was clearly extraordinarily fast, far beyond anything humans could directly measure with their own senses. Think about how you'd measure the speed of something in everyday life. If you want to know how fast a car is going, you measure how far it travels in a specific amount of time. Drive 100 kilometers in 1 hour, and your speed is 100 kilometers per hour. Simple, but this requires being able to accurately measure both distance and time. For slow-moving objects, this is easy. A person walking across a room takes several seconds to cross maybe 5 meters. You can time that with a stopwatch. For faster objects, you need better tools, but the principle remains the same. Light, if it moves at all, moves incomparably faster than anything humans had experienced for most of history. The fastest thing most people encountered for thousands of years was a galloping horse managing perhaps 50 or 60 kilometers per hour. An arrow might reach 150 kilometers per hour. These speeds were measurable with crude timing methods. Light, as we now know, travels at about 300,000 kilometers per second, not per hour, per second. That's roughly 1.08 billion kilometers per hour, or about 671 million miles per hour. It's so fast that it crosses the distance a horse gallops in 1 hour in about 300ths of a second, faster than you can blink. No wonder the ancients couldn't measure it. The technology required wouldn't exist for more than 2,000 years after they first asked the question. The first serious attempt to measure light speed came from Galileo Galilei in 1638. His method was ingenious in its simplicity. He and an assistant stood on distant hilltops at night, each holding a shuttered lantern. Galileo would uncover his lantern, sending light toward his assistant. When the assistant saw the flash, he would uncover his own lantern, sending light back to Galileo. Galileo tried to measure the time delay between uncovering his lantern and seeing his assistant's response. The experiment failed, or more precisely, it succeeded in showing that if light had a finite speed, that speed was too fast to measure with human reaction times over distances of a few kilometers. The delay Galileo tried to measure would have been about 20 microseconds, 20 millionths of a second, for a distance of 3 kilometers. Human reaction time is roughly 200 milliseconds, about 10,000 times longer. He couldn't possibly detect the light travel time beneath the noise of his own reflexes. But Galileo drew the right conclusion. He wrote that if light speed wasn't infinite, it was extraordinarily rapid. He understood the limitation of his method and recognized that answering the question would require a different approach. The breakthrough came from an unexpected direction. In 1676, Danish astronomer Ole Rømer wasn't trying to measure light speed at all. He was trying to improve predictions for eclipses of Jupiter's moon. Io Jupiter has 4 large moons visible through telescopes. As they orbit Jupiter, they periodically pass into Jupiter's shadow, disappearing from view in an eclipse. Rømer made careful observations and created tables predicting when these eclipses would occur. But he noticed something strange. When Earth was moving toward Jupiter in its orbit, the eclipses happened slightly earlier than predicted. When Earth was moving away from Jupiter, they happened slightly later. The pattern was consistent and related to Earth's position. Rømer realized what was happening. Light from Jupiter took time to cross the space between Jupiter and Earth. When Earth was closer to Jupiter, light had less distance to travel and arrived sooner. When Earth was farther away, light had more distance to travel and arrived later. The difference wasn't huge, at most about 22 minutes total across Earth's orbit, but it was measurable and consistent. By knowing the change in distance as Earth orbited the Sun, roughly 300 million kilometers from one side of Earth's orbit to the other, and measuring the time difference of about 22 minutes, Romer could calculate light's speed. His answer was about 220,000 kilometers per second, roughly 75% of the actual value. Not bad for a first measurement made in 1676 using observations of Jupiter's moons. The calculation wasn't quite right because Romer didn't know the exact size of Earth's orbit, but the principle was sound. Light had a finite speed, and that speed could be measured. This was revolutionary. Light, which seemed instantaneous, actually took time to travel. You didn't see things as they were, but as they had been when the light left them. The sun you see is the sun as it was 8 minutes ago. The stars you see at night are as they were years or centuries or millennia ago. You live in a universe of delayed information where everything you perceive happened in the past. Think about what this means for your everyday experience. When you look at your hand in front of your face, you're seeing it as it was about 1/1000th of a second ago. The delay is so infinitesimally small, it might as well be instantaneous, but it's not zero. There's a gap, however tiny, between the moment light bounces off your hand and the moment it reaches your eye. For objects across a room, the delay is a few billionths of a second. For a friend standing 30 meters away, it's 1/10 millionth of a second. For a mountain kilometers away, it's several millionths of a second. These delays are far too small to notice, but they're real. You're always seeing the past, never the present. This becomes more significant over larger distances. When you watch the moon, you see it as it was 3 seconds ago. If the moon suddenly vanished, you wouldn't know for over a second. You'd continue seeing it, a ghost image from the past, until the last photons that left before it disappeared finally reached your eyes. When you look at the sun, you see it as it was 8 minutes and 20 seconds ago. The sun could have exploded 8 minutes ago, and you wouldn't know yet. You'd continue to see it shining peacefully for another 20 seconds before the darkness arrived. This might seem like a curious fact, but it has profound implications. Information cannot travel faster than light. If the sun exploded, that information, that change in reality, would propagate outward at light speed. Not just the light itself, but everything. The gravitational effects, the solar wind, all of it. Earth wouldn't just go dark. It would suddenly stop feeling the sun's gravity at the same moment, flying off in a straight line instead of continuing its orbit. This suggests something deep about the nature of reality. Light speed isn't just about light. It's about information, about causality, about the maximum rate at which one event can influence another. It's woven into the structure of space and time themselves. After Romer's discovery, other scientists refined the measurement. In 1728, James Bradley measured stellar aberration, the apparent shift in star positions caused by Earth's motion through space combined with light's finite speed. His calculation gave about 301,000 kilometers per second, very close to the modern value. In the 19th century, physicists developed methods to measure light speed over terrestrial distances. In 1849, Hippolyte Fizeau used a rotating toothed wheel to chop a light beam into pulses. He sent the light to a distant mirror and back, adjusting the wheel's rotation speed until returning light passed through the next gap in the wheel. From the wheel's rotation rate and the distance traveled, he calculated light speed at about 315,000 kilometers per second. The following year, Léon Foucault improved the method using a rotating mirror instead of a toothed wheel and got 298,000 kilometers per second, even closer to the true value. By the late 1800s, it was clear that light traveled at a specific measurable speed of approximately 300,000 kilometers per second. This raised new questions. Speed is usually measured relative to something. When you say a car moves at 100 kilometers per hour, you mean relative to the road. When you say a plane flies at 900 kilometers per hour, you mean relative to the air or the ground. What was light speed measured relative to? Was there some medium through which light waves traveled? the way sound waves travel through air, physicists proposed the existence of a luminiferous ether, an invisible substance filling all of space, through which light propagated as waves. If the ether existed, Earth's motion through it should create an ether wind, similar to how a car moving through still air creates a wind from the car's perspective. Light traveling with the ether wind should move faster relative to Earth than light traveling against it. In 1887, Albert Michelson and Edward Morley conducted an extraordinarily precise experiment to detect this ether wind. They used an interferometer, a device that splits light into two perpendicular beams, sends them along perpendicular paths, then recombines them. If one beam traveled slightly faster or slower than the other due to ether wind, the recombined light would show interference patterns. The experiment found nothing. No matter which direction they oriented their apparatus, no matter what time of day or year they conducted the measurement, light traveled at the same speed in all directions. There was no ether wind. Light's speed appeared to be constant regardless of Earth's motion. This was baffling. How could light maintain a constant speed regardless of the observer's motion? If you're on a train moving at 100 kilometers per hour and you shine a flashlight forward, shouldn't the light move at 300,000 kilometers per second plus 100 kilometers per hour relative to the ground? Apparently not, according to the Michelson-Morley experiment. The result made no sense within the physics of the time. Various explanations were proposed, but none were satisfactory. The puzzle sat unsolved for nearly 2 decades until a young patent clerk named Albert Einstein offered a radical solution that would transform our understanding of space, time, and the very nature of reality. But before we get to Einstein's insight, let's establish exactly what light is. Because understanding the nature of light helps explain why it behaves so strangely at these enormous speeds. Before we can truly understand why nothing moves faster than light, we need to understand what light actually is. And this turns out to be one of the strangest stories in all of physics. For most of human history, light seemed simple. It was just brightness, the opposite of darkness, something that let you see. But when scientists started investigating light carefully, they discovered something far stranger than anyone expected. In the 1600s, 2 competing theories emerged. Isaac Newton believed light was made of tiny particles, like invisible bullets shooting through space. His rival, Christian Huygens, argued light was a wave, like ripples on a pond. And for the next 2 centuries, physicists argued back and forth. Sometimes, light acted like particles. It traveled in straight lines, it bounced off mirrors at predictable angles. When it hit your eye, it seemed to arrive in discrete little packets of energy. Newton's particle theory explained all of this perfectly. But other times, light acted like waves. It bent around corners. It created interference patterns where 2 light beams could meet and cancel each other out, creating darkness. Try doing that with bullets. It had different colors that corresponded to different wavelengths. Huygens's wave theory explained these phenomena beautifully. For a long time, the particle theory dominated, mainly because Newton was Newton. But in 1801, a British scientist named Thomas Young performed an experiment that seemed to settle the question once and for all. Young's double-slit experiment was elegantly simple. He shone light through 2 narrow slits and observed the pattern on a screen behind them. If light was made of particles, you'd expect to see 2 bright lines on the screen, one behind each slit. Instead, he saw multiple bands of light and darkness. This is exactly what waves do. When water waves pass through 2 openings, they spread out and overlap, creating regions where the waves reinforce each other, bright bands, and regions where they cancel each other out, dark bands. Young's experiment seemed to prove conclusively that light was a wave, but waves need something to wave in. Water waves travel through water. Sound waves travel through air. So what did light waves travel through? Scientists invented an answer: the luminiferous ether. They imagined space was filled with an invisible, massless substance that transmitted light waves. This ether had to be everywhere in the vacuum of space, even passing through solid objects, yet it had to be rigid enough to transmit waves at 300,000 kilometers per second. The whole idea was rather desperate, but it was the only way to make wave theory work. And then, in 1887, Michelson and Morley tried to detect this ether and found nothing. Their famous null result was devastating. If light was a wave and there was no ether, then what was waving? The answer came from an unexpected direction. In the 1860s, a Scottish physicist named James Clerk Maxwell was studying electricity and magnetism. These had been considered separate phenomena, but Maxwell discovered they were intimately connected. When he wrote down the mathematical equations describing how electric and magnetic fields interact, something extraordinary emerged. The equations predicted that changing electric fields would create magnetic fields, and changing magnetic fields would create electric fields. These fields could sustain each other, creating a self-propagating wave that required no medium to travel through. And when Maxwell calculated how fast these electromagnetic waves would move, he got 300,000 kilometers per second. It was light. Light wasn't particles. Light wasn't waves in a medium. Light was electromagnetism. Light was a ripple of interlocking electric and magnetic fields, propagating through space itself, needing nothing to travel through. Think about that for a moment. Every time you turn on a lamp, you're creating oscillating electric and magnetic fields that race outward at the speed of light. The visible light your eyes detect is just electromagnetic radiation with wavelengths between about 400 and 700 nanometers. Radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, gamma rays, these are all the same phenomenon, just with different wavelengths. Your cell phone signal, electromagnetic waves at about 2 gigahertz frequency. The heat you feel from a fire, infrared electromagnetic radiation. The X-ray that images your bones, high energy electromagnetic waves. The visible light from this screen, electromagnetic waves in the narrow band your eyes evolved to detect. All of it travels at the same speed. 299,792,458 meters per second in vacuum. We've measured it so precisely, we've actually defined the meter in terms of light speed. The meter is now officially the distance light travels in 1,299,792,458th of a second. Maxwell's equations unified light, electricity, and magnetism into a single elegant framework. It was one of the greatest achievements in physics history, and it raised a profound question. If light is an electromagnetic wave that doesn't need a medium, what determines its speed? When sound travels through air, its speed depends on the properties of air, temperature, pressure, density. When waves travel through water, their speed depends on properties of water. But electromagnetic waves don't travel through anything. So why do they travel at 300,000 kilometers per second? Why not faster? Why not slower? Maxwell's equations provided a mathematical answer. The speed of light, c, emerges from two fundamental constants. The permittivity of free space, SL, which describes how electric fields behave in vacuum, and the permeability of free space, mu, which describes how magnetic fields behave in vacuum. The relationship is beautifully simple. C equals sine 1 srot root d0 mu. These constants aren't arbitrary. They're built into the fundamental structure of reality. The speed of light isn't something light chooses. It's something the universe enforces. It's a property of space itself. And here's where things get truly strange. If you measure the speed of light while sitting still, you get 299,792,458 meters per second. If you measure it while racing toward a light beam at half the speed of light, you still get 299,792,458 meters per second. If you measure it while racing away from a light beam, you still get the same number. This is nothing like our everyday experience. If you throw a baseball forward from a moving train, the ball's speed relative to the ground is your throwing speed plus the train's speed. But light doesn't work that way. Light speed is always the same, regardless of how you or the light source are moving. This was the puzzle Michelson and Morley had uncovered. Earth orbits the Sun at 30 kilometers per second. That's fast. If light traveled through a stationary ether, we should measure different light speeds depending on whether we're moving toward or away from the light source. But we don't. Light speed is constant. For 2 decades, physicists wrestled with this paradox. Some tried to modify Maxwell's equations. Some suggested the ether was dragged along with Earth. Some proposed increasingly bizarre explanations. And then, in 1905, a 26-year-old patent clerk in Switzerland had a different idea. Instead of trying to explain why light speed was constant, Albert Einstein simply accepted it as a fundamental postulate and worked out the consequences. What he discovered would revolutionize our understanding of space, time, matter, energy, and reality itself. The speed of light wasn't just a speed limit, it was a window into the deepest structure of the universe. Let's see what Einstein discovered. In June 1905, Albert Einstein submitted a paper to the journal Annalen der Physik with a modest title, On the Electrodynamics of Moving Bodies. It would become one of the most important scientific papers ever written. Einstein started with 2 simple postulates. First, the laws of physics are the same in all inertial reference frames. In plain language, if you're moving at constant velocity, whether sitting still or cruising through space at 1,000,000 kilometers per hour, physics works exactly the same way. Second, the speed of light in vacuum is constant for all observers, regardless of their motion or the motion of the light source. That second postulate was the revolutionary one. It was counterintuitive. It seemed to violate common sense, but Einstein took it seriously and followed the logic wherever it led. And where it led was stranger than anyone imagined. Let's start with time. We tend to think time is universal, a cosmic clock ticking at the same rate everywhere. 1 second for you is 1 second for me, is 1 second for someone in a distant galaxy. Time is absolute. But Einstein realized, if light speed is constant for all observers, time cannot be absolute. Here's why. Imagine you're on a train platform, and I'm on a train moving past you at high speed. I have a light clock, just 2 mirrors, one on the floor and one on the ceiling, with a pulse of light bouncing between them. Each round trip of the light pulse is 1 tick of my clock. From my perspective on the train, the light travels straight up, bounces off the top mirror, and travels straight down. The distance is, let's say, 3 meters. At 300,000 kilometers per second, this takes 0.000000001 seconds, 10 nanoseconds. That's 1 tick of my clock. But from your perspective on the platform, you see something different. You see my train rushing past. The light doesn't travel straight up and straight down. From your perspective, it travels diagonally. Because the train is moving, it has to cover a longer path to get from floor to ceiling and back. Now here's the crucial point. The speed of light is the same for both of us. That's Einstein's second postulate. Light doesn't travel faster just because the train is moving. So if the light has to travel a longer path from your perspective, diagonally instead of straight up and down, it must take more time. In other words, my clock ticks slower from your perspective than from mine. This isn't an illusion. This isn't about observation tricks or signal delays. Time itself, the actual passage of time, is running slower for me, from your perspective, because I'm moving relative to you. This phenomenon is called time dilation, and it's real. It's been measured countless times with atomic clocks on airplanes, satellites, particle accelerators, and GPS systems. When things move fast, their clocks literally run slower compared to stationary clocks. The equation is remarkably simple. T equals sine t/frat 1 minus v quadred c quadred. where t is the stationary time, t-tar is the moving time, v is velocity, and c is the speed of light. That term in the denominator, rat1 minus v quadred c quadred, shows up everywhere in relativity. It's called the Lorentz factor, and it describes how much time slows down or space contracts at different speeds. At everyday speeds, the effect is tiny. A car traveling at 100 kilometers per hour experiences time dilation of about 1 part in a trillion. You'd have to drive for 100 years to lose a single second. But at high speeds, the effect becomes dramatic. At 90% light speed, time slows down by a factor of 2. 3 clocks run at 43% of normal rate. At 99% light speed, time slows by a factor of 7. Clocks run at 14% of normal rate. At 99% light speed, time slows by a factor of 70. There's a famous thought experiment called the twin paradox. One twin stays on Earth. The other travels to a star 10 light-years away at 99% the speed of light, then returns. From Earth's perspective, the trip takes about 20 years, but for the traveling twin, due to time dilation, only 8 years pass. When the traveling twin returns, they're 17 years younger than their stay-at-home sibling. This isn't science fiction, it's observed reality. Muons, subatomic particles created in Earth's upper atmosphere, have a lifetime of 2 microseconds. They're created about 10 kilometers up and travel toward Earth at 99.8% light speed. In 2 microseconds, even at that speed, they should only travel about 660 meters before decaying. They shouldn't reach the ground. But they do, in huge numbers. Why? Because from our perspective, their clocks are running slow due to time dilation. Their 2 microsecond lifetime is stretched to about 33 microseconds, giving them time to reach the surface. We've measured this thousands of times. Time dilation is as real as gravity. But time dilation is only half the story. Einstein realized that if time is relative, space must be relative too. Imagine I'm on that same high-speed train, holding a meter stick horizontally in the direction of motion. From my perspective, the stick is exactly 1 meter long. I can measure it. But from your perspective on the platform, watching the train zoom past, something strange happens. Due to the requirements of constant light speed, the meter stick appears contracted in the direction of motion. It looks shorter than 1 meter. This is called length contraction. The formula is lay equals sign L tixad 1 minus v quadred c quadred. At 90% light speed, lengths contract to 43% of their rest length. That meter stick looks 43 centimeters long. At 99 Beck stars, 99% light speed, it contracts to 4 centimeters. This resolves the muon paradox from another angle. From the muon's perspective, time isn't dilated. Their 2 microsecond lifetime is normal. Instead, the distance to Earth's surface is contracted. The 10-kilometer atmosphere appears only about 280 meters thick at their speed, so they can easily cross it before decaying. 2 perspectives. Same outcome. This is the beauty of relativity. Space and time adjust in perfectly coordinated ways to ensure the speed of light remains constant for all observers. But Einstein wasn't finished. He realized that space and time aren't separate things. They're aspects of a single entity. Space-time. We live in a 4-dimensional universe, 3 spatial dimensions plus 1 time dimension, and how you split space-time into space and time depends on how you're moving. Think of it this way. You can describe a location on Earth using latitude and longitude. But those are just coordinates, human inventions for measuring position. The actual surface of Earth doesn't care about your coordinate system. Similarly, space-time is the fundamental reality, and how you divide it into space measurements and time measurements depends on your reference frame. This led Einstein to his most famous equation, E equals sign mc quadred, energy equals mass times the speed of light squared. This equation says that mass and energy are equivalent. They're different forms of the same thing. You can convert mass into energy. That's what happens in nuclear reactions and stars. In principle, you can convert energy into mass. That's what happens in particle accelerators. But notice, the conversion factor is c quadrate, the speed of light squared. That's a huge number, about 90 quadrillion in SI units. This means a tiny amount of mass contains enormous energy. 1 kilogram of matter, if converted entirely to energy, would release 90 petajoules, roughly equivalent to the energy from 20 million tons of TNT. That's about the same as the largest nuclear weapon ever tested. This is why the speed of light matters so much. It's not just how fast light travels. It's woven into the conversion factor between mass and energy. It's part of the fundamental structure of space-time itself. And here's where we start to see why nothing can move faster than light. When an object moves, it has kinetic energy, energy of motion. In classical physics, kinetic energy is 1/2 mv quadrude, double the speed, and you quadruple the kinetic energy. Straightforward. But Einstein's relativity changes this. The correct formula for kinetic energy is Ke equals sine mc quadrude, 1 fine v quadrude, 1. At low speeds, this reduces to the classical formula. But at high speeds, something remarkable happens. As velocity approaches the speed of light, that denominator, ρ quadrude, 1 fine v quadrude, the kinetic energy approaches infinity. To accelerate a massive object to light speed would require infinite energy. Not a lot of energy, not more than all the energy in the universe. Infinite energy. Literally impossible. But wait, it gets stranger. According to relativity, as an object speeds up, its relativistic mass increases. The faster you go, the more massive you become, from the perspective of a stationary observer. At 90% light speed, your mass is 2-3 times your rest mass. At 99% light speed, it's 7 times. At 99% light speed, it's 70 times. As you approach light speed, your mass approaches infinity, and accelerating infinite mass requires infinite force. This is why nothing with mass can reach light speed. The universe itself prevents it. The faster you go, the harder it gets to go even faster. Light speed is an asymptotic limit. You can get closer and closer, but you can never quite reach it. We've tested this in particle accelerators. The Large Hadron Collider accelerates protons to 9,999,991%, the speed of light. At this speed, the protons have 7,460 times their rest mass. Each proton carries as much kinetic energy as a flying mosquito, which doesn't sound like much until you remember protons are about 10 quadrillion times smaller than mosquitoes. The energy density is staggering, and we can't push them faster. We pump in more energy, and they gain more mass, but their speed barely increases. We're up against a fundamental limit of the universe. But here's the beautiful paradox. While nothing with mass can reach light speed, light itself has no mass. Photons, particles of light, are massless, and massless particles must always travel at exactly light speed. They can never be stationary. They can never go slower or faster. From light's perspective, if we could somehow ride along with a photon, the journey from the sun to Earth would take 0 time. The photon is created in the sun's core, and from its perspective, it instantly arrives at your eye. The 8-minute journey we observe is due to our time frame, not the photons. In a sense, photons don't experience time at all. They exist outside the normal flow of cause and effect. Every photon that's ever existed, from the cosmic microwave background 13.8 billion years ago to the light hitting your screen right now, experienced 0 elapsed time from their own perspective. This is the heart of Einstein's revolution. Space is relative. Time is relative. Mass and energy are equivalent, and the speed of light is the universal constant that binds it all together, not just a speed limit, but a fundamental feature of reality itself. But this raises an even deeper question. Why is the speed of light the cosmic speed limit? Is it just an arbitrary rule, or is there something deeper going on? Let's explore that next. So we know nothing with mass can reach light speed, but why? Is the speed of light just an arbitrary cosmic rule, like a universal traffic law? Or is there something deeper, something fundamental that makes it necessary? The answer lies in the structure of causality itself. The speed of light isn't just a speed limit. It's the speed of causality. It's the speed at which cause and effect propagate through the universe. Let's think about what causality means. When you flip a light switch, the light turns on. Cause precedes effect. When you drop a glass, it falls and shatters. Cause, then effect. The entire universe operates on this principle. Events happen in sequence, with causes coming before their effects. But here's the crucial insight from relativity. The order of events which happens first can depend on your reference frame. Two events that seem simultaneous to you might not be simultaneous to someone moving relative to you. This works fine as long as the events are separated in space. If two distant stars explode at the same moment from your perspective, someone moving past you at high speed might see one explode before the other. That's okay. There's no causal connection between the explosions. One didn't cause the other, so the order doesn't matter. But what if there is a causal connection? What if one event causes another? Einstein realized that for causality to work, for the universe to make sense, there must be a cosmic speed limit. If information could travel infinitely fast, you could have situations where effects precede causes in some reference frames. You could potentially affect your own past. The entire logical structure of the universe would collapse. The speed of light is that limit. It's the maximum speed at which any signal, any information, any causal influence can propagate. And this isn't arbitrary. It's a requirement for the universe to be causally consistent. Here's a thought experiment. Imagine you could send a signal faster than light. You send a message to a distant star instantaneously. From your perspective, the message arrives at the same moment you send it. No delay, but now consider someone moving at high speed relative to you. Due to relativity of simultaneity, events that are simultaneous in your frame happen at different times in theirs. From their perspective, your instantaneous signal arrives at the distant star before you sent it. If they could also send faster than light signals, they could send a message back to you, and it could arrive before you sent your original message. You could receive a response before asking the question. Effect before cause. This isn't just strange, it's logically impossible. It would allow closed causal loops, situations where an event is its own cause. You could, in principle, send a message to your past self, telling you not to send the message. Paradox. The only way to prevent this is to ensure no signal, no information, no causal influence can travel faster than light. The speed of light is the speed of causality itself. Think of spacetime as having a structure, a causal structure. Every event in spacetime has a light cone. The past light cone contains all events that could have influenced this event. The future light cone contains all events this event could influence. And the boundary of the light cone, the surface, expands at the speed of light. You can only affect things inside your future light cone. You can only be affected by things inside your past light cone. Events outside your light cone are causally disconnected from you. They're in your elsewhere. Nothing happening right now on a planet 1,000 light years away can affect you for at least 1,000 years. You're causally isolated by the speed of light. This is fundamental. It's not a limitation of technology. It's not that we haven't figured out how to go faster. It's that faster than light is fundamentally incompatible with causal logic. But there's more. The speed of light is also tied to the structure of spacetime itself, to how space and time relate to each other. In special relativity, we describe spacetime using something called the Minkowski metric. This is just a mathematical way of measuring distances in spacetime. But it reveals something profound. Space and time aren't quite equivalent. there's a minus sign in the metric that distinguishes time from space. The space-time interval between two events is $do quadrate = c $do quadrate minus $do y quadrate minus $do y quadrate. Notice the minus signs. Space dimensions get subtracted. This makes space-time fundamentally different from ordinary four-dimensional space. It's a pseudo-Euclidean geometry, not Euclidean. And that speed of light term c appears explicitly in the equation. It's the conversion factor between time and space. It's what connects the time dimension to the spatial dimensions. Without it, space-time wouldn't have the structure it has. In fact, you can think of the speed of light as the exchange rate between space and time. 1 second equals 299,792,458 meters of space-time. 1 meter of space-time equals 3 nanoseconds of time. They're different dimensions, but they're connected by c. This is why physicists sometimes say the speed of light is better understood as unity, as 1, not 299,792,458. If you measure time in meters, the distance light travels in that time, then c = 1. Space and time have the same units. The speed of light isn't a speed, it's a dimensionless ratio built into space-time geometry. From this perspective, asking why is the speed of light 299,792,458 meters per second is like asking why is there 161 kilometers in a mile. It's just a conversion factor between units. The deep question is, why does space-time have this structure, with time distinguished from space by this particular ratio? And the answer seems to be, because otherwise, causality wouldn't work. Because otherwise, the universe wouldn't be logically consistent. Now you might wonder, what about quantum mechanics? Quantum particles can be entangled, and when you measure one, the other responds instantly, even if they're light years apart. Doesn't this violate the cosmic speed limit? It doesn't. This is one of the most misunderstood aspects of quantum mechanics. Quantum entanglement doesn't transmit information faster than light. It can't be used to send signals. When you measure an entangled particle, you get a random result. The distant particle's measurement will be correlated with yours, but the correlation is only apparent after you compare results, which requires classical communication at light speed or slower. You can't use entanglement to transmit a message faster than light. Causality is safe. In fact, there's a deep result in quantum field theory, the theory that combines quantum mechanics and special relativity that proves this rigorously. It's called the no-signaling theorem. Measurements on one particle cannot affect outcomes of measurements on a distant particle in a way that allows faster-than-light communication. The theory mathematically forbids it. But here's something even stranger. The speed of light isn't just the maximum speed for matter and information. It's also the speed of gravity. When Einstein extended special relativity to include gravity, creating general relativity in 1915, he discovered that gravity isn't a force in the traditional sense. It's a curvature of spacetime caused by mass and energy. The sun doesn't pull Earth with an invisible force. The sun curves spacetime, and Earth follows the curved path. But this curvature can't respond instantly. If the sun suddenly vanished, it won't. But imagine, Earth wouldn't immediately fly off in a straight line. The change in spacetime curvature would propagate outward at the speed of light, as a gravitational wave. Earth would continue orbiting for 8 minutes, the light travel time from Sun to Earth, before the gravitational change arrived. We've detected these gravitational waves. In 2015, LIGO observed ripples in spacetime from colliding black holes 1.3 billion light-years away. The waves arrived traveling at exactly the speed of light within measurement precision of 1 part in 1015. Gravity propagates at light speed. This makes sense from a deeper perspective. In general relativity, all massless fields propagate at the speed of light. Electromagnetic waves, photons, are massless. Gravitational waves, gravitons, if they exist as particles, are massless. They must travel at c. And here's a profound unity. The speed of light isn't really about light. It's about the structure of space-time. It's about causality. It's about the maximum speed at which anything, matter, energy, information, forces, can propagate through the universe. We could call it the speed of space-time, or the speed of causality, or the speed of information. We call it the speed of light for historical reasons, because we first measured it using light. But it's far more fundamental than photons. It's the universe's way of maintaining logical consistency. It's what prevents effects from preceding causes. It's what keeps time as a coherent dimension, flowing from past to future. It's what gives space-time its structure. This is why nothing can go faster, not because light is special, but because causality is fundamental. And this leads to a fascinating consequence. The speed of light defines the structure of the observable universe. Since the Big Bang happened 13.8 billion years ago, and nothing can travel faster than light, we can only see objects whose light has had time to reach us. The observable universe has a radius of about 46 billion light-years. It's larger than 13.8 billion light-years because of cosmic expansion. But that's another topic. Beyond that radius is the unobservable universe. Not because it's dark or hidden, but because light from those regions hasn't had time to reach us yet. The speed of light creates a cosmic horizon. We're causally disconnected from anything beyond that horizon. It might as well not exist from our perspective. In a sense, the speed of light defines the boundary of our universe, not the physical universe, but the universe we can observe, interact with, and be influenced by. It's the ultimate limit on our cosmic perspective. Some physicists have speculated about faster-than-light possibilities, wormholes, warp drives, exotic matter. We'll discuss these later, but every proposal requires violating known physics or invoking hypothetical substances that may not exist. None provides a simple workaround to the cosmic speed limit, because it's not really a limit, it's a consequence. It falls out of the requirement that the universe be causally consistent, that causes precede effects, that time flows forward, that the past stays past, and the future stays future. The speed of light is the speed at which reality propagates, and that's why nothing can move faster. Not because the universe is being restrictive, but because the very concepts of motion and speed and causality only make sense within the framework the light speed limit creates. You can't go faster than the speed of light. For the same reason, you can't go north from the North Pole. It's not a limitation, it's a boundary condition on the structure of reality itself. So what happens if you try? Let's imagine you're an astronaut in a spacecraft, and you decide to test the cosmic speed limit. You have an incredibly powerful engine, maybe a fusion drive, maybe antimatter propulsion, maybe something even more advanced, and you start accelerating. At first, everything seems normal. You feel the acceleration pushing you back into your seat. Your speedometer climbs 1,000 kilometers per second, 10,000, 100,000. You're now traveling at a third the speed of light. Impressive. But then you notice something odd. You're using the same amount of fuel, applying the same thrust, but your speed isn't increasing as quickly as it should. According to Newtonian physics, constant force should produce constant acceleration. But that's not what's happening. You push harder. You divert more power to the engines. Your speed creeps up, 150,000 kilometers per second, half the speed of light. Then 200,000 kilometers per second, 2/3 light speed. But now something stranger is happening. From your perspective inside the ship, your accelerometer shows constant acceleration. You feel a steady push. But observers back on Earth, watching your velocity, see your speed increasing more and more slowly. You're asymptotically approaching light speed, but never quite reaching it. What's going on? From Earth's perspective, your relativistic mass is increasing. At half light speed, your mass is about 1/15 times your rest mass. At 90% light speed, it's 2-3 times. At 99% light speed, it's 7 times. The same thrust that accelerated you easily at low speeds is now struggling against your increased mass. But from your perspective, something else is happening. Your mass feels normal to you. Instead, the entire universe in the direction you're traveling appears contracted. Distances shrink. The distance to your destination star, which was 10 light-years away when you started, now appears only 4 light-years. At 99% light speed, it would appear less than 5 light-years. You're experiencing length contraction in real time. The universe is literally squashing in front of you. And time is weird too. Your onboard clock ticks normally from your perspective, but when you radio back to Earth, you find that years have passed there while only months passed for you. Time dilation is making your journey shorter from your perspective, so you keep accelerating. 99% light speed, 99%. Each increment requires more and more energy. From Earth's perspective, your mass is now hundreds, then thousands, then millions of times your rest mass. You're pumping enormous amounts of energy into the engines, but your speed barely budges. Let's do the math. To accelerate a 1000-ton spacecraft to 90% light speed requires about 3 × 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ TNT, or 15,000 of the largest nuclear weapons ever built. To reach 99% light speed, you need 5 × 10⁻1 joules, 4 times more energy for a 9% increase in speed. To reach 99% light speed, you need 2 × 10⁻1 joules, more than all the energy humanity has ever produced in all of history. And it just gets worse. At 999% light speed, you'd need 10⁻1 joules. That's more energy than the sun produces in a month. The function is exponential, approaching infinity as you approach light speed. There's no amount of energy in the universe that could push you to exactly light speed, because you'd need infinite energy. But let's say you somehow manage to get to 99,999% light speed. You're now in a very strange realm. From Earth's perspective, your mass is 2,236 times your rest mass. Time on your ship is passing at 1/2236th. The rate of Earth time, and the entire visible universe in front of you is contracted to a narrow cone of extreme blue shifted light. This is called relativistic beaming. Light from objects ahead of you gets compressed and blue shifted toward higher frequencies. Light from behind you gets red shifted and stretched. At extreme speeds, the universe doesn't just look contracted, it looks completely distorted, with most of the visible light crammed into a bright, narrow cone directly ahead. And there are practical dangers. Space isn't empty. There are stray hydrogen atoms, dust particles, cosmic rays. At low speeds, these are harmless, but at relativistic speeds, they become deadly. A single hydrogen atom, when you're traveling at 99% the speed of light, hits your spacecraft with the kinetic energy of a grain of sand moving at several kilometers per second. That's enough to punch through metal. A small dust grain would hit with the energy of a large bomb. This is a real problem for any hypothetical relativistic spacecraft. At high speeds, even the tenuous interstellar medium becomes a dangerous radiation hazard and erosion threat. You'd need massive shielding, which adds mass, which requires even more energy to accelerate. But let's ignore the practical problems and focus on the fundamental physics. What if you kept accelerating indefinitely? Would you ever reach light speed? No, never. No matter how much energy you pump in, no matter how powerful your engines, you'll asymptotically approach light speed but never reach it. From your perspective on the ship, something subtle is happening. You feel constant acceleration. Your speedometer shows ever-increasing velocity relative to your starting point. But the universe keeps length contracting ahead of you. And your clock keeps slowing down relative to the outside universe, in exactly the right proportions to ensure that whenever you measure the speed of light from your ship using your contracted rulers and slowed clocks, you always get 299, 792,458 meters per second. Light is still moving away from you at the same speed, always. This is the genius of relativity. Space and time adjust themselves dynamically to ensure the speed of light remains constant. You can't catch up to a light beam because the very act of trying, accelerating to higher speeds, causes space and time to transform in ways that keep light speed constant relative to you. It's like running on a treadmill that speeds up to match your pace. No matter how fast you run, the treadmill adjusts and you stay in the same place relative to it. Now, particles in accelerators experience this every day. Protons in the Large Hadron Collider are accelerated to 999,999,991% the speed of light. They're moving so fast that they circle the 27-kilometer ring 11,245 times per second. Their relativistic mass is 7,460 times their rest mass. But here's the thing, from the proton's perspective, they're not moving at all. From their reference frame, they're stationary, and it's the accelerator ring that's moving around them. And due to length contraction, the 27-kilometer ring appears only about 6 meters long. They're not traveling far from their own perspective. This is the relativity of motion. There's no absolute reference frame. You can't say who's really moving. The proton is moving from the lab's perspective. The lab is moving from the proton's perspective. Both perspectives are equally valid, but what both perspectives agree on, the proton can never reach light speed. From the lab's perspective, it would require infinite energy. From the proton's perspective, light is still moving away at full light speed, no matter how much the proton accelerates. The universe enforces the speed limit not through some cosmic police force, but through the deep logical structure of space-time itself. Now, there's one more fascinating consequence of all this. Because time dilation and length contraction increase without limit as you approach light speed, a hypothetical traveler could, in principle, cross vast cosmic distances in their own lifetime. If you could sustain 1g acceleration, comfortable Earth gravity, you'd reach 95% light speed in about 3 years of ship time. In 10 years of ship time, you'd be at 99,996% light speed. At that speed, you could travel 100 light years in what feels like about 10 years, thanks to time dilation. From your perspective, you could cross the galaxy in a human lifetime. You could reach Andromeda in 30 years of ship time. You could even in principle reach distant galaxy clusters. But, and this is crucial, when you returned, millions of years would have passed on Earth. Everyone you knew would be long dead. Civilizations would have risen and fallen. You'd be traveling into the deep future with no way back. This is the one-way nature of relativistic travel. Time dilation works in your favor for crossing distances, but there's no reverse gear. You can skip forward through time, but you can never go back. So trying to exceed light speed doesn't just fail, it's conceptually incoherent. The faster you go, the more the universe adjusts to prevent you from catching light. It's not a wall you hit. It's an asymptote you approach but never reach. An unreachable horizon built into the geometry of space-time. And that's what happens when you try. The universe simply won't let you win. Not because it's mean, but because the very idea of winning this race doesn't make sense within the rules of space-time. But are there any loopholes? Any clever tricks? Any ways to travel faster than light without actually moving faster than light? So nothing can move through space faster than light. The math is clear. The experiments confirm it. The logic is airtight. But physicists are creative. And over the past century, they've explored theoretical loopholes. Ways you might travel faster than light without technically breaking the rules. Some are purely speculative. Some might be impossible. But they're worth understanding because they reveal just how carefully constructed the cosmic speed limit really is. Let's start with the most famous loophole: wormholes. A wormhole is a hypothetical tunnel through space-time. Imagine space-time as a flat sheet. You want to travel from point A to point B, which are far apart on the sheet. The normal route is a straight line across the surface. But what if you could fold the sheet so A and B touch, then punch a hole connecting them? You could step through the hole and arrive instantly without traveling the distance across the surface. That's the idea behind a wormhole, formerly called an Einstein-Rosen bridge. Einstein's general relativity equations allow for these structures mathematically. They're valid solutions to the field equations. The concept is tantalizing. Instead of traveling faster than light through space, you take a shortcut through space-time itself. You never exceed light speed locally, within your own reference frame. You're moving slower than light. But you arrive at a distant location faster than light could get there by the normal route. It's like digging a tunnel through a mountain instead of driving over it. You're not moving faster. You're just taking a shorter path. But here's the problem. For a wormhole to stay open, to be traversable, you need something called exotic matter. This is matter with negative energy density, and we've never found any. Ordinary matter has positive energy density. It curves spacetime in a way that attracts things together. That's gravity. But exotic matter would curve spacetime oppositely. It would push things apart. It would hold the wormhole throat open against the tendency of spacetime to collapse. Without exotic matter, a wormhole would snap shut instantly. You couldn't get through before it pinched off, probably crushing you to infinite density in the process. Not an appealing travel method. Now, quantum field theory does allow for negative energy densities in certain situations. The Casimir effect, for example, creates a tiny region of negative energy between two metal plates. But the amounts are minuscule, and there's a quantum inequality that limits how much negative energy you can accumulate and for how long. Specifically, the quantum inequalities show that the more negative energy you try to concentrate and the longer you try to maintain it, the more it's constrained by compensating positive energy elsewhere. It's like trying to dig a hole by piling dirt next to it. The deeper the hole, the higher the pile. The amount of negative energy needed to hold open a human-sized wormhole is staggering. Early estimates suggested you'd need more negative energy than the total positive mass energy in the observable universe. Later refinements reduced this somewhat, but we're still talking about amounts far beyond anything we can create or manipulate. Some physicists have proposed that advanced civilizations might harvest negative energy from the quantum vacuum using enormous Casimir plates, metal surfaces separated by nanometers but spanning thousands of kilometers. Even this speculative mega-engineering would likely fall short of what's needed. And there's another problem. Even if you could create a wormhole, you couldn't use it for faster-than-light travel initially. Here's why. To create a wormhole connecting two locations, you'd first need to move one end of the wormhole to the distant location. And that movement happens at slower than light speed. So if you wanted a wormhole from Earth to a star 100 light-years away, you'd need to transport one end there, which would take more than 100 years. Only after that could you use the wormhole for instant travel. You can't use it to get somewhere faster than light unless someone already got there the slow way first. It's like building a tunnel under the mountain. Yes, once built, it's faster than going over the mountain. But building it takes time. The first trip is always the slow one. Wormholes, even if possible, don't let you violate causality on the first journey. They might let you create a useful rapid transit network across the galaxy, but only after centuries or millennia of setup time. And you'd need to maintain them constantly against collapse, pumping in exotic matter perpetually. There's also a disturbing possibility. Some calculations suggest that a traversable wormhole could be converted into a time machine. If you took one end of a wormhole and accelerated it to near light speed, then brought it back, time dilation would cause that end to age more slowly than the stationary end. Now the two ends exist at different times. Step through, and you travel to the past. But this is where the universe seems to object. When physicists model this scenario carefully, They find that quantum effects tend to destabilize the wormhole at the exact moment it becomes a time machine. Vacuum fluctuations build up catastrophically, potentially destroying the wormhole in a burst of energy. This is related to Hawking's chronology protection conjecture, the idea that the laws of physics conspire to prevent time travel and causality violations. We don't know if this conjecture is true, but the universe seems committed to preventing grandfather paradoxes. Then there's the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. This is an even wilder idea, moving space itself. The concept is this: what if you could contract space in front of your spacecraft and expand it behind you? You'd surf on a wave of space-time, like a surfer on an ocean wave. Locally, you're not moving through space, you're stationary within your bubble, and space is moving around you. Your local speed never exceeds light speed, so you don't violate relativity. But from an outside perspective, you could cross vast distances quickly. It's a brilliant loophole. The speed limit applies to motion through space, but space itself can expand or contract at any rate. In fact, during cosmic inflation right after the Big Bang, space expanded exponentially faster than light. This doesn't violate relativity, because nothing was moving through space. Space itself was growing. So could an Alcubierre drive work? The math checks out in general relativity. It's a valid solution to Einstein's field equations. Alcubierre showed that if you arrange matter and energy in a very specific configuration, creating a region of contracted space in front of the ship and expanded space behind, you could move the bubble containing the ship at faster than light speeds relative to distant observers. But once again, there's a catch. You need exotic matter, huge amounts of it. The original calculations suggested you'd need a mass energy equivalent to Jupiter, but in negative form, to create a bubble large enough for a small spacecraft. Later refinements by physicists like Chris van den Broek reduced the energy requirements by suggesting a different bubble geometry, very small inside, larger outside. This brought the energy requirement down to something like the mass of the Sun. Still absurdly large, but at least not requiring negative energy exceeding the mass of a gas giant. But even this assumes we can create and control exotic matter, which we can't, and there are other problems. How do you start and stop the warp bubble? To create the bubble, you need to manipulate space-time around your ship. But to do that, you'd need to send signals or place equipment ahead of your ship, which requires traveling faster than light, which is what you're trying to achieve in the first place. It's a bootstrapping problem. While you're inside the warp bubble, you're causally disconnected from the edge of the bubble and the outside universe. You can't steer, you can't accelerate or decelerate. You can't receive sensor data about what's ahead. You're essentially surfing blind, unable to control your destination once in motion. Some calculations suggest that the interior of an Alcubierre bubble would be bathed in Hawking radiation, high-energy particles created by the extreme space-time curvature. This radiation could be lethal to any occupants and might even destroy the ship. And perhaps most problematically, physicist William Hiscock showed that arriving at your destination would release all the energy accumulated in the bubble's geometry in a catastrophic burst. The energy from the contracted space in front and expanded space behind would be dumped into the destination region, potentially in the form of high-energy particles or radiation. Some calculations suggest this burst would have enough energy to sterilize the target star system, so you'd arrive at your destination instantly and promptly incinerate everything there, including yourself. Not ideal. These aren't just engineering challenges. They're fundamental physics problems that we don't know how to solve and which may not have solutions at all. Then there's quantum entanglement, which we mentioned earlier. When two particles are entangled, measuring one seems to instantly affect the other, no matter the distance. Einstein called this spooky action at a distance and was deeply troubled by it. He thought it meant quantum mechanics was incomplete. But as we discussed, entanglement can't be used to send information faster than light. The results of measurements are random, You can't control what result you get, so you can't encode a message. The correlation between entangled particles is only apparent after you compare results through normal, slower-than-light communication. Let's make this concrete. Suppose you have two entangled particles, and you take one to Alpha Centauri while I keep the other on Earth. We agreed beforehand to measure our particles at the same time. When I measure mine, I get a random result, let's say spin up. Quantum mechanics guarantees that when you measure yours, you'll get the opposite result, spin down. But here's the key. I can't control whether I get spin up or spin down. It's truly random, so I can't use this to send you a message. I can't encode hello by forcing my particle to be spin up or down in a pattern. All I can do is measure and get random results. Only later, when you return to Earth or we compare results via radio, do we discover the correlation. The entanglement is real. It's been verified in thousands of experiments, but it's useless for faster-than-light communication. There are no-go theorems in quantum mechanics proving this rigorously. Any attempt to use entanglement for faster-than-light signaling fails. The universe protects causality at the quantum level just as surely as at the relativistic level. What about tachyons, hypothetical particles that always move faster than light? These pop up occasionally in speculative physics and science fiction. The interesting thing about tachyons is that if they existed, they'd have to always move faster than light. Just as normal particles can never reach light speed from below, tachyons could never slow down to light speed from above. Light speed would be a barrier from both sides. Tachyons would have bizarre properties. Their mass would be imaginary, not in the sense of being fictitious, but in the mathematical sense involving the square root of negative numbers. Their energy would decrease as they sped up and increase as they slowed down. To bring a tachyon to rest would require infinite energy. But tachyons cause serious causality problems. If tachyons existed, you could use them to send messages to your own past. Here's how. You send a tachyon signal to a distant location. Due to relativity of simultaneity, there's a reference frame in which that signal arrives in the past. An observer in that frame could send a tachyon signal back to you, and it would arrive before you sent your original signal. This creates closed time-like curves, causal loops, where an event is its own cause. You could send a message to your past self, telling yourself not to send the message. Classic grandfather paradox. Most physicists consider tachyons unphysical. When they appear in theoretical calculations, it's usually a sign that the theory is unstable or incomplete, not that faster-than-light particles really exist. In quantum field theory, a tachyonic field indicates vacuum instability. The system will decay to a more stable state where tachyons don't exist. There's another interesting theoretical possibility: cosmic strings. These are hypothetical one-dimensional defects in spacetime, like cracks in ice as it freezes. They'd be incredibly thin, far thinner than an atom, but immensely dense, with masses of billions of tons per meter of length. Cosmic strings might have formed in the early universe during phase transitions, similar to how cracks form in ice. They'd be stretched across vast distances, possibly even spanning the observable universe. If cosmic strings exist, and if you could manipulate them in the right configuration, some calculations suggest you might create closed time-like curves, paths through spacetime that loop back on themselves. Travel along such a path, and you'd arrive at your own past. The mechanism is subtle. Two cosmic strings moving past each other at high speed create a region of strange spacetime geometry. If you fly your spacecraft in a loop around this configuration in just the right way, you could theoretically complete the loop before you started arriving back in your own past. This is time travel, which is related to faster-than-light travel through relativity. If you can go backward in time in one reference frame, there's another reference frame where you're traveling faster than light through space. So cosmic strings might offer another loophole. But once again, cosmic strings are hypothetical. We've never observed one. Astronomers have searched for their gravitational lensing effects. They'd create distinctive patterns in background starlight, but found nothing. If cosmic strings exist, they must be rare, and even if they exist, manipulating them to create closed time-like curves would require moving them at nearly light speed and arranging them in very specific configurations, an engineering challenge beyond imagination. You'd need to grab objects with the mass of mountains compressed into threads thinner than atoms and fling them around at relativistic speeds with precision. And once again, quantum effects likely intervene. Just as with wormhole time machines, calculations suggest that vacuum fluctuations would build up catastrophically in closed time-like curves, possibly preventing their formation or destroying them immediately. There's a pattern here. Every time we find a potential loophole in relativity, every way to potentially travel faster than light or travel backward in time, we discover either that it requires exotic matter or exotic conditions we can't create, or that quantum effects or other phenomena prevent it from working, or that it leads to logical paradoxes. The universe seems deeply committed to maintaining causality. Every loophole comes with enormous barriers, requirements for negative energy, quantum instabilities, engineering impossibilities, or logical contradictions. This suggests that the speed of light limit isn't just a rule, it's a deeply structural feature of reality. It's not that we haven't found the trick yet, it's that there is no trick. The universe is causally consistent, because it must be, and the speed of light is the mechanism that enforces that consistency. Hawking's chronology protection conjecture captures this idea. It suggests that the laws of physics prevent time travel and causality violations, that whenever a theory allows closed time-like curves or faster-than-light travel, quantum effects or other phenomena intervene to prevent them from actually forming or being used. We don't know if this conjecture is provably true, but it's supported by several observations. First, we don't see causality violations in nature. Causes always precede effects. Second, every time we calculate what happens when you try to create a time machine or faster-than-light pathway, the physics seems to conspire against you. Third, we've never received a message or visitor from the future, which is odd if time travel becomes possible at any point in the future of our universe. The universe appears to be causally consistent as a matter of principle, not accident, and the speed of light is central to that consistency. But even if we can't break the light speed barrier, we can still ask, what role does light speed play in shaping the universe we observe? How does this cosmic speed limit affect the cosmos itself? The speed of light doesn't just limit how fast we can travel. It shapes the entire structure of the observable universe. It determines what we can see, how we see it, when we see it, and even what exists from our perspective. Let's start with the most profound consequence. We see the universe as it was, not as it is. When you look at the moon, you're seeing it as it was, 1.3 seconds ago, the time it takes light to travel from the moon to Earth. When you see the sun, you're seeing it as it was, 8 minutes and 20 seconds ago. If the sun exploded right now, it won't. But imagine we wouldn't know for over 8 minutes. We'd continue seeing the sun shining normally, casting light and warmth on Earth, until the light from the explosion arrived. Then the sky would flare brilliant. And 8 minutes later, the shockwave of solar wind and particles would arrive, and Earth's fate would be sealed. Look at the nearest star system, Alpha Centauri, and you're seeing it as it was 4.37 years ago. That star might have developed a massive solar flare last week, sending radiation toward Earth, and we wouldn't know yet. Or maybe a rogue planet passed through the system 3 years ago, and we won't see it for another year. The night sky is a museum of ancient light. Every photon that enters your eye has traveled for years, centuries, millennia, or even billions of years to reach you. You're literally seeing history, not reading about it, but actually observing the past as it was. The bright star Sirius, the jewel of the winter sky, you're seeing it as it was 9 years ago. The beautiful star Betelgeuse in Orion's shoulder, That's light from 700 years ago, from when Marco Polo was exploring China and the Mongol Empire stretched across Asia. The light left that star before the Renaissance, before the printing press, before Columbus sailed. The Andromeda Galaxy, our nearest large galactic neighbor, is 2.5 million light-years away. When you look at Andromeda, visible to the naked eye on a dark night as a faint smudge, you're seeing it as it was 2.5 million years ago, around the time our ancestors were just beginning to use stone tools, when Homo habilis walked the African savanna. The Andromeda you see is long gone. It exists now in a state you won't observe for another 2.5 million years. Stars have been born and died in that galaxy since the light you're seeing left. The entire structure has rotated, evolved, changed, but from our perspective, we're seeing an ancient snapshot, frozen in time by the finite speed of light. The most distant galaxies we observe with powerful telescopes are seen as they were over 13 billion years ago, less than 1 billion years after the Big Bang itself. We're seeing them as primordial, star-forming galaxies, young, blue, irregular, actively birthing the first generations of stars from vast clouds of hydrogen and helium. Those galaxies are surely very different now, 13 billion years later. They've evolved into mature elliptical or grand spiral galaxies, their star formation long since settled into a steady state, or perhaps stopped entirely. But we can't see that. We're separated by billions of light years and billions of years of time. The galaxies we observe exist in a state long past. This creates a strange and profound situation. The universe has a horizon, the cosmic light horizon, because the universe has a finite age. 13.8 billion years, and light takes time to travel. We can only see objects whose light has had time to reach us since the Big Bang. But here's where it gets tricky. You might think the observable universe has a radius of 13.8 billion light-years, corresponding to the age of the universe. It doesn't. It has a radius of about 46 billion light-years. Why the discrepancy? Because the universe has been expanding while the light traveled toward us. A photon that's been traveling for 13.8 billion years was emitted by an object that was much closer to us at the time of emission. But during the photon's journey, space itself stretched, carrying that distant object farther away. By now, that object is 46 billion light-years away. This is one of the most counterintuitive aspects of cosmology. The expansion of space isn't like objects moving through space, it's space itself growing. Imagine dots on the surface of a balloon. As you inflate the balloon, the dots move apart, but they're not moving across the surface. The surface itself is expanding. And space can expand faster than light without violating relativity, because nothing is moving through space faster than light. The distance between distant galaxies increases faster than light speed, but that's due to expanding space between them, not their motion through space. In fact, there are galaxies right now that are receding from us faster than light due to cosmic expansion. We can still see some of them, the ones whose light was emitted long ago when they were closer and space was expanding more slowly. Their ancient light has had time to reach us, but we'll never be able to reach those galaxies now, no matter how fast we travel, because they're already beyond our causal horizon and getting farther every second. The speed of light, combined with cosmic expansion, divides the universe into nested regions. First, there's the observable universe. Everything we can see in principle, given infinite time and infinitely powerful telescopes. This is everything within our past light cone, everything whose light has reached us. Then there's the reachable universe, a smaller region containing only galaxies we could reach if we left today traveling at near light speed. This is shrinking over time due to accelerating expansion. And finally, there's the causally connected universe, the region that can affect us or that we can affect. This is our true cosmic neighborhood. Everything beyond it is in a real sense in a separate universe from ours. We'll never interact with it. We can't send signals to it. We can't receive signals from it. It might as well not exist from our perspective. This has profound philosophical implications. There might be infinitely many galaxies beyond our cosmic horizon. There might be other intelligent civilizations out there, other Earths, other versions of you reading this script in a distant galaxy. But they're forever causally disconnected from us. The speed of light creates a fundamental isolation, a cosmic loneliness. And this isolation is getting worse. The universe's expansion is accelerating, driven by something we call dark energy, a mysterious component that makes up about 70% of the universe's energy density and acts as a kind of anti-gravity, pushing space to expand faster and faster. Distant galaxies are receding from us ever faster, galaxies that are currently just barely visible at the edge of our observable universe will eventually disappear beyond our cosmic horizon as they recede faster than light. Due to accelerating expansion, the light they're emitting now will never reach us. In trillions of years, if current trends continue, only our local cluster of galaxies, the Milky Way, Andromeda, and a few dozen smaller companions, all bound together by mutual gravity, will remain visible. The rest of the universe will have receded beyond the cosmic horizon, unreachable and invisible forever. Future civilizations trillions of years from now will live in a much lonelier universe, a small cluster of galaxies surrounded by eternal darkness with no evidence that a larger cosmos ever existed. They might develop cosmology and conclude that their cluster is the entire universe. They'd have no way to know about the vast cosmos beyond their horizon. In a sense, we're lucky to live when we do. We can see the cosmic web of galaxies, the large-scale structure of the universe, the afterglow of the Big Bang. Future astronomers won't have that privilege. But the speed of light isn't just a limitation, it's also a powerful tool. Astronomers use light's finite speed to study cosmic history in a way no other science can match. When we observe distant galaxies, we're not just seeing them at great distances, we're seeing them at early times. The farther we look, the further back in time we see. Distance equals time. The universe becomes a time machine, with every telescope a portal to the past. By studying galaxies at different distances, we're studying different epochs of cosmic history. We see galaxies 13 billion years ago, when they were young and actively forming stars. We see them 10 billion years ago, as they matured and began forming spiral structures. We see them 5 billion years ago, as star formation slowed and galaxies began to redden with age. And we see nearby galaxies today in their current state. It's like having a time-lapse video of cosmic evolution spread across space. We can watch the universe grow up from its infancy to its current middle age. We can see how galaxies form, how they merge, how they evolve. We can study the history of star formation across cosmic time, watching the universe light up with newborn stars in the early epochs, then gradually dim as star formation slows. Distance equals time. Light speed is the frame rate of cosmic history. The most distant light we can observe is the cosmic microwave background radiation from 380,000 years after the Big Bang, when the universe first became transparent to light. Before that moment, the universe was so hot and dense that photons couldn't travel freely. They scattered constantly off free electrons in a dense fog of plasma. But when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, suddenly photons could travel freely. The universe became transparent and light streamed outward in all directions. That light has been traveling for 13.8 billion years, and it's still reaching us today, redshifted by cosmic expansion into microwave wavelengths. This light, the cosmic microwave background, is the oldest light in the universe. It carries information about the early cosmos. Its temperature, 2.7 Kelvin today, but nearly 3000 Kelvin when emitted. Its density, its composition, and most remarkably, its structure. Tiny fluctuations in temperature across the sky reveal the seeds of all cosmic structure. The slight density variations that eventually grew into galaxies and galaxy clusters. By studying the CMB, we're observing the universe as an infant, We're seeing the initial conditions from which everything evolved. And we can do this only because light has a finite speed. If light traveled infinitely fast, we'd see everything as it is right now, all at once. We'd have no window into the past. Cosmology as we know it would be impossible. The speed of light creates cosmic archaeology. Every observation is an excavation of the past. The speed of light is also crucial for measuring cosmic distances. Astronomers use a variety of techniques, collectively called the cosmic distance ladder, each rung depending on light's properties and travel time. For nearby stars, we use parallax, the apparent shift in a star's position as Earth orbits the Sun. This relies on knowing Earth's orbital speed and distance from the Sun, both measured using light travel times. For more distant objects, we use standard candles, objects with known intrinsic brightness. By comparing their apparent brightness to their intrinsic brightness, we can calculate their distance using the inverse square law, which depends on how light spreads out as it travels. Cepheid variable stars pulse with a period directly related to their luminosity. Measure the period, and you know the luminosity. Measure the apparent brightness, and you can calculate the distance. This technique works out to tens of millions of light years. For even greater distances, we use Type 1a supernovae, exploding white dwarf stars that reach a nearly uniform peak brightness. They're bright enough to see across billions of light years, and their consistent brightness makes them excellent distance markers. And finally, for the most distant objects, we use redshift, the stretching of light waves due to cosmic expansion. The more redshift, the more the universe has expanded since the light was emitted, and the farther away the object is. Every technique depends on light, its speed, its properties, its behavior. Without light, we'd be blind to the cosmos, unable to measure distances or study distant objects. And light speed determines how quickly information propagates through the universe. When a supernova explodes, the light reaches us years or millennia later, depending on distance. When gravitational waves from colliding black holes ripple through space-time, they propagate at light speed, carrying information about the collision. When a gamma-ray burst erupts from a distant galaxy, perhaps from a hypernova or colliding neutron stars, the gamma rays travel at light speed. Every signal, every messenger from the cosmos is limited by the speed of light. This creates a natural ordering to our knowledge. We learn about cosmic events in the order their light reaches us, not the order they occurred. A supernova might explode in Andromeda Galaxy today, but we won't know for 2.5 million years. From our perspective, it hasn't happened yet. The past, present, and future are scrambled across cosmic distances, layered by light travel time. This also means that right now, throughout the universe, countless events are occurring that we can't yet observe. Stars are exploding. Planets are forming around young stars. Galaxies are colliding in spectacular mergers. Black holes are devouring matter and spitting out jets of particles at near light speed. Maybe somewhere civilizations are broadcasting signals or building vast structures. But their light hasn't reached us yet. These events are in our future light cone, events that will affect us or that we'll observe eventually, but not yet. They're happening now in their local time frame, but not yet in ours. And there are events that happened in the distant past, billions of years ago, that we're only observing now. The light from a galaxy merger 10 billion years ago is just now reaching Earth, entering our telescopes. The event is long finished. The merged galaxy has settled into its new elliptical form billions of years ago. The stars born in the merger starburst have lived and died, but we're only now watching the merger unfold, seeing it for the first time. This is the strange nature of a universe with a finite light speed. The cosmos is layered in time, with different regions visible at different epochs, and events scattered across billions of years, arriving at our telescopes in a sequence determined by distance and light travel time. If you could somehow observe the entire universe simultaneously, see every galaxy as it is right now, in some absolute cosmic present, it would look completely different from what we observe. Nearby galaxies would look mostly similar to how we see them, with only a few years or millennia of difference. But distant galaxies would be unrecognizably evolved, billions of years older than we observe them, their spiral structures matured or disrupted, their star formation long since peaked and declined. But we can't see that. We're trapped in our local present, our observations limited by the speed of light, seeing a universe that's part present and part deep past, layered according to distance, like the rings of an ancient tree. The speed of light doesn't just limit our travel, it limits our knowledge. It creates a fundamental horizon on what we can know about the universe at any given moment. And it makes cosmology a historical science, where observation is always observation of the past, where looking outward is looking backward in time. In a way, we're all historians when we look at the night sky. Every star, every galaxy, every nebula we observe is history. Recent history for nearby objects, ancient history for distant ones, and the earliest history for the most distant galaxies and the cosmic microwave background. The universe is a vast library of light, and the speed of light determines how fast we can read it. Each photon is a message from the past, a letter written long ago and only now being opened. And we're reading billions of letters every second, piecing together the story of the cosmos from the scattered messages arriving at our eyes and telescopes. This is both a limitation and a gift. We can't see the universe as it is, but we can see it as it was, across all of cosmic time. We're denied a snapshot of the present, but given a movie of history. And that's not a bad trade. So far, we've talked about why nothing can move faster than light. But there's an interesting twist. In certain situations, things do move faster than light. Not through space, but in other ways. And understanding these exceptions helps us appreciate just how fundamental and carefully enforced the cosmic speed limit really is. Let's explore what happens at or beyond light speed, or what appears to happen. First, there's space itself. As we mentioned, the expansion of the universe can make distant galaxies recede from us faster than light. This isn't motion through space, it's space itself, expanding. And general relativity places no limit on how fast space can expand. During cosmic inflation, a brief period right after the Big Bang, lasting perhaps 10 to the minus 32 seconds, space expanded exponentially fast, increasing in size by a factor of at least 10 to the power of 26 in a tiny fraction of a second. That's a trillion times larger, in less time than it takes light to cross the diameter of a proton. Regions of space that were once close enough to be in causal contact, close enough to touch, were suddenly separated by billions of light years. They were ripped apart faster than light could cross the gap between them. This didn't violate relativity because nothing moved through space faster than light. The expansion was an increase in the fabric of space itself. If you were standing on a planet during inflation, though matter as we know it didn't exist yet, you wouldn't feel any motion, you wouldn't be accelerated or pushed. Locally, physics would work completely normally, but the distance to distant objects would grow faster than light speed could traverse. It's like dots drawn on the surface of a balloon. When you inflate the balloon, the dots move apart, but they're not moving across the surface. The surface itself is expanding beneath them. No dot moves faster than light across the surface, but distant dots can separate faster than light due to the expansion of the surface between them. This is happening today too, just much more slowly. The universe is still expanding, and sufficiently distant galaxies are receding from us faster than light due to that expansion. Galaxies beyond about 14 billion light-years are currently receding faster than light. We can still see some of them because their light was emitted long ago when they were closer and the expansion rate was different. But we'll never be able to reach them. Even if we left today traveling at 99 9,999% of light speed for billions of years, because they're already too far away and getting farther faster than we could travel. The speed of light limits motion through space, but not the rate at which space itself can grow. These are fundamentally different things. Then there's the interior of black holes. Once you cross a black hole's event horizon, the point of no return, you're inside a region where space itself is falling toward the singularity faster than light. Not moving through space, but space itself flowing inward like a river. From this perspective, you can't escape a black hole, not because the gravity is too strong to overcome, but because you'd need to move outward through space faster than light to counter the inward flow of space itself. It's like trying to swim upstream in a river, flowing faster than you can swim. You're not trapped by force, you're trapped by geometry. No matter which direction you point your rocket, no matter how powerful your engines, every direction leads toward the singularity. Up, down, left, right, all directions inside the event horizon point inward. The singularity isn't somewhere you might go, it's somewhere you must go, as inevitable as tomorrow. And tomorrow is the right word, because inside a black hole, the singularity isn't a place in space, it's a moment in time. Time and space trade roles in a strange sense. The radial direction becomes time-like. Just as you can't avoid moving forward in time in normal space, you can't avoid moving inward toward the singularity inside a black hole. At the singularity itself, our understanding breaks down completely. Densities and curvatures become infinite, or at least beyond our ability to describe with current physics. All the matter that fell into the black hole is compressed into a point of zero volume, or perhaps into a structure we can't comprehend without a theory of quantum gravity. This is truly beyond the speed of light, a realm where our normal concepts of speed and motion don't apply, where the structure of space-time itself becomes singular and breaks down. There are also phenomena that create the illusion of faster-than-light motion without actually violating the cosmic speed limit. One is called superluminal motion, observed in certain astrophysical jets. When a quasar or active galactic nucleus shoots out a jet of material at near light speed, and that jet is aimed almost directly toward us, we can observe an optical illusion where blobs of material in the jet appear to move sideways faster than light across our field of view. Here's how it works. Imagine a blob of material is ejected from the quasar at 99% of light speed at a slight angle toward Earth. Let's say 10 degrees off our line of sight. The blob travels outward, and as it does, it emits light in our direction, but it's chasing its own light. The light emitted later doesn't have much farther to travel to reach us than the light emitted earlier, because the blob is catching up to its earlier light. From our perspective, watching over the course of years, we see the blob move a large angular distance across the sky in a very short time, because the light from the start and end of that movement arrive at Earth with only a brief delay between them, much less than the actual time the blob took to travel. The blob appears to move faster than light sideways across our view, but it's an illusion, a projection effect. The actual motion is slower than light. It's just that the geometry and light travel times create the appearance of superluminal motion. We've observed this in dozens of quasar jets and active galactic nuclei. Some appear to move at 3 times light speed, 5 times, even 10 times. But it's always a projection effect, perfectly consistent with relativity once you account for the viewing angle and light travel delays. Another interesting case is phase velocity versus group velocity. This is the speed at which a wave pattern moves, as opposed to the speed at which energy or information moves. Imagine you're watching a stadium wave at a sports event. The wave pattern travels around the stadium very quickly, much faster than any individual person could run around the stadium. But no person is moving fast. Each person just stands and sits at the right moment. The pattern moves fast, but the information, the signal from person to person, travels much slower. In certain optical media, you can create situations where the phase velocity, the speed of the wave pattern, exceeds the speed of light. The peaks and troughs of the wave seem to move faster than light through the material. But no energy, no information, no actual disturbance is traveling faster than light. The group velocity, the speed at which information propagates, is always slower than light in vacuum. This has been demonstrated in laboratories. Physicists have created pulses of light, where the peak of the pulse appears to exit a material before it fully entered. The pulse seems to travel faster than through the material. But careful analysis shows no information is transmitted faster than light. It's a pulse reshaping effect, where the material absorbs the front of the pulse and amplifies the tail, creating the appearance that the peak moved faster than it should. Then there are quantum effects, like quantum tunneling. A particle can appear on the other side of a barrier without having traveled through the intervening space in a classical sense. The time this takes is called the tunneling time, and some experiments suggest it's shorter than you'd expect from light-speed transit across the barrier width. Does this mean quantum tunneling is faster than light? Not really. The particle doesn't have a definite path or speed during tunneling. It's in a quantum superposition of states. And importantly, no information can be transmitted faster than light using tunneling. When you try to use tunneling to send a signal, the process always includes delays that ensure the signal propagates at light speed or slower. There's also the Scharnhorst effect, a theoretical prediction from quantum field theory that in certain modified vacuum states, light might travel slightly faster than c. This would occur between conducting plates in a Casimir configuration where the quantum vacuum is altered by boundary conditions. The effect is incredibly tiny, perhaps 1 part in 10 to the 36th in realistic configurations. And it's not clear it could be used to send information faster than light in a way that violates causality. The modified vacuum has different properties. So faster than c might not mean what we think. But it's an interesting edge case in extreme quantum situations. In all these cases, cosmic expansion, black hole interiors, superluminal jets, phase velocities, quantum tunneling, modified vacuums, we're either dealing with apparent motion rather than real motion, or motion of something other than matter or information through space, or motion in such extreme regimes that normal concepts break down. The fundamental rule holds: no information, no energy, no causal influence can propagate through space faster than light. The universe is deeply, profoundly committed to this principle. This makes sense from a deeper perspective. The speed of light isn't really about light. It's about causality, the speed at which cause and effect propagate. And causality is what makes the universe comprehensible, predictable, logical. If information could travel faster than light, we'd have situations where effects precede causes. We'd have paradoxes, contradictions, breakdowns of logic. The universe would be fundamentally chaotic and incomprehensible. There would be no reliable laws of physics, because effects could influence their own causes, creating circular causation. Instead, we have a universe with a consistent causal structure, where the future is determined by the past, where causes lead to effects in a logical sequence, where the arrow of time points consistently forward, where memory works and prediction is possible, and the speed of light is the mechanism that enforces this. It's the maximum rate of cause and effect. It's the speed at which reality propagates from one event to the next. In a sense, the speed of light is the speed of existence itself. Events don't just exist in some abstract sense. They exist in relation to other events, connected by causal links that propagate at light speed or slower. The universe isn't a static collection of objects frozen in time. It's a dynamic network of causes and effects, spreading outward from every event at light speed, weaving the fabric of space-time, creating the structure of reality. This is why nothing can move faster, because faster would mean breaking the causal links that hold the universe together. It would mean existing outside the logical structure of space-time. It would mean being disconnected from reality itself. The speed of light isn't a barrier keeping us trapped. It's the foundation that makes reality coherent. It's not a limitation. It's the organizing principle that allows the universe to make sense. Section 10. Closing. What it all means. 500 words. So we've traveled through the nature of light, the structure of space-time, the limits of motion, and the edges of reality. We've explored the history of how we discovered light's speed, the physics of why nothing can exceed it, the theoretical loopholes that turn out not to be loopholes at all, and the role light speed plays in shaping the observable cosmos. And at the end of it all, we return to the simple question we started with: why can't anything move faster than light? The answer, as we've seen, is that the question itself is slightly wrong. It's not that things can't move faster than light in some arbitrary sense, as if the universe posted a speed limit sign and enforces it with cosmic traffic police. It's that faster than light doesn't make sense as a concept within the structure of our universe. The speed of light isn't a speed limit imposed on the universe from outside. It's a property of the universe itself, built into the structure of space-time, woven into the relationship between space and time, embedded in the way causality works, fundamental to the conversion between mass and energy. Asking why nothing can go faster than light is like asking why you can't travel north from the North Pole, or why a triangle's angles can't sum to more than 180 degrees in flat geometry, or why you can't have a square circle. It's not a restriction, it's a consequence of the framework, the geometry, the logical structure you're working within. Light speed, represented by that letter C in countless physics equations, is the conversion factor between space and time. It's the maximum rate at which causality propagates from event to event. It's the speed at which massless particles must travel, and the asymptotic limit that massive particles approach but never reach. It's the speed of gravity, the speed of information, the speed at which the consequences of any action ripple outward through space-time. And it's woven into everything, into Einstein's famous equation, E equals mc squared, where c squared converts between mass and energy, into the Lorentz transformations that describe how time dilates and space contracts, into the curvature of space-time around massive objects, into the event horizon of black holes, into the expanding edge of the observable universe, into the propagation of electromagnetic waves and gravitational waves. Every equation, every phenomenon, every structure in physics is touched by the speed of light. Remove it, and the universe doesn't just work differently, it doesn't work at all. The logical coherence collapses, causality breaks down, the clear distinction between past and future dissolves. The universe becomes paradoxical, self-contradictory, incomprehensible. This is what makes the speed of light so profound. It's not an arbitrary constant that happens to be 299,792,458 meters per second because of some accident of cosmic history. It's a fundamental organizing principle of reality. It's what makes the universe, a coherent, causal, comprehensible whole, rather than a chaotic jumble of disconnected events without logic or structure. We are beings who exist in time, whose thoughts are sequences of causes and effects, whose memories preserve the past and whose intentions aim toward the future. We are causal creatures living in a causal universe, and the speed of light is what creates that causality. It's what separates past from future, cause from effect, here from there. It's what gives time its arrow and space its structure. It's what allows events to influence each other in a logically consistent way, creating the web of causation that underlies all of physical law. So when we look up at the stars on a clear night and realize that their light has traveled for years or centuries or millennia to reach us, we're not just seeing distant objects scattered across space. We're seeing the causal structure of the cosmos made visible, the network of light-speed connections that binds the universe together into a coherent whole, the threads of causation woven across space-time. The speed of light is the speed of reality itself, and that's not a limitation. That's not something to overcome or escape. That's the foundation of everything. That's what allows existence to be logical, comprehensible, beautiful. Now rest easy. Let the universe unfold at its own pace, at its own speed, the speed of light, the speed of causality, the speed of reality. Let causes lead to effects in their natural sequence. Let time flow forward from past to future. Let the cosmos be what it is. A place where things make sense, where logic holds, where the past stays past and the future remains ahead. The speed of light is not a barrier keeping us trapped in ignorance or limitation. It's a gift, the gift of causality, the gift of comprehensibility, the gift of a universe that operates by consistent laws, that can be understood, that makes sense. And in a universe that makes sense, we can rest, we can observe, we can understand, we can appreciate the profound beauty of a cosmos structured by simple, elegant principles. Principles like the constancy of light speed, the relationship between space and time, the conservation of energy, the forward flow of causality. So sleep peacefully, knowing the universe is held together by light, not just the light of stars, but the deeper principle that light represents. The principle that information propagates at a finite speed, the principle that cause precedes effect, the principle that reality is woven together into a unified, comprehensible whole. Good night. Let light travel at its own pace. Let the universe be what it is. Let causality guide the flow of time. And rest in the knowledge that nothing needs to move faster than light, because light speed is exactly what it needs to be for the universe to work, for reality to make sense, for existence itself to be possible. Good night.